Okay, let's give this a shot. So I'm going to walk you through this front piece, and then you get to go through the back piece. And if you have extra time, you can work on your assignment from the other day. So it says consider the function f of x equals x to the third plus 2x squared minus 1 over the interval -3 to +2. Now let me ask you first. It says find the critical points of the function, or critical numbers. Where do critical numbers exist? Wherever the derivative is equal to 0. Where else? Wherever the function is undefined or not differentiable. Now, I have a polynomial here. Is it continuous? Yep, these are continuous. Is it differentiable everywhere? Yes, it is. So the only pieces that will be of critical values to me will simply be where the derivative is equal to 0. So that's the first thing I'm going to do. Yes. What's that? Right here? Oh, okay. F prime of x is equal to 3x squared. Bryce be a dummy. That's worse than stupid Luke. Okay, so we got f prime of x is equal to 3x squared plus 4x. In order to find the critical points, I will do what? Set it equal to 0 and solve. How will I solve for this equal to 0? What will I do? Factor out an x. Very good. I'll be left with 3x plus 4. So it looks like I have two spots. So x is equal to and -4/3 are my two spots. Now, somebody think in your mind and suppose what maybe happens at those spots. Slope is probably 0. Those would be called local mins and maxes. I'm guessing we probably have local mins and maxes there. But before we get to that, we're going to draw this out. It says identify local min and max and absolute min and max. So in order to find local and absolute min and max, what do I need to do? It would help if I graphed it. So let's just, before we actually draw the graph out, let's get a general idea of what this looks like. We'll plug it in our calculator. X to the third plus 2x squared minus 1. And I'm going to view it on a 10 by 10 viewing window. So I'm going to zoom standard, zoom 6. And I get a cubic equation that looks approximately like that. So does it look like I have local min and max at about those spots? I sure do. So I know that I have local mins and maxes around there. I should also, how do I check though for absolute? What pieces do I need to check? Again, look at that we're over this given interval. We're not talking about this whole graph. We're just talking about the graph from -3 to +2. So what do I need to check to be able to identify absolute min and max? I need to check the, starts with E, endpoints. Very good. Endpoints. So if you want to find absolute min and max of that graph, we'll sketch it in just a second here. But I must check local min and max. I must also, or these points right here, these critical numbers, I must also check the endpoints. So I'm going to do f of -3, f of -4/3, f of 0, and f of 2. We're going to see what kind of outputs we get. So I'm going to take this function, and I'm going to go to my table, and I'm going to punch in some points. -3 gives me -10. -4/3 gives me 0.19. 0 gives me -1, and 2 gives me 15. That is my endpoints, because specified that I'm only talking about the graph over that given interval. Now the graph does go to negative infinity to positive infinity, but that would be over a domain of negative infinity to positive infinity, which is not the case here. So as I look here, is -10 an absolute min or max or a local min or max? It is the smallest value of all of these, so it must be an absolute min. Yep. At a location of -3, the graph has a value of -10. And we'll graph this so you can actually see it as it takes shape. 0.19. Is it an absolute max? Is it a local max? It is a local max. I have f of 0 is -1. That will be a local min. And I have f of 2 is 15. That will be a absolute max. It could be. But in this situation, since it's an endpoint, it's not. Because at a local min or max, the derivative will be equal to 0. And the derivative is not equal to 0 at 2. It's only equal to 0 at 0 and -4/3. Those are those points. We're almost ready to sketch. It says, what is the average rate of change of the function over the given interval? Average rate of change, what does that tell you to do? What is average rate of change? Slope. Slope. If I want to find the slope over this entire interval, this is referencing the mean value theorem. The average rate of change would be f of b minus f of a over b minus a, which is your slope formula. What was f of b? F of 2 is 15 minus, what is f of a? -10 over 2 minus -3. So I've got 25 over 5, which is 5. So on average, the slope is 5 over that entire interval. Now, there's some points on the graph where it's much greater than 5. There's other points on the graph where it's lower than 5. It's actually negative. But from beginning to end, the average rate of change is 5. Just like you could drive in a car, your average speed could be 50, but you might go as much as, say, 70, and you might go as slow as, say, 0 if you're stopped somewhere, okay? So same type of thought. So let's actually sketch a graph now, okay? And this is the best I could do. I worked really hard to try to find good problems. I could have done better, but it does, not everything fits on here, unfortunately. But that's okay. We'll start with -2. What is my, or is it -3? What do I got up there? -3. So what's the value at -3? So I go 1, 2, 3, 4, 5. So that's where I start. Okay. And I have a local max at -4/3, which is -1.33, and it makes it up to like 0.19, right? So I'd have a spot right there. And then at 0, it goes down to -1. And then how about at 2? It goes all the way up to 15. Okay. So that's our graph. I can draw it. Come up here, do this little local min thing, local max thing. Make it up there. And that's a general sketch of my graph over that given interval. Okay? Now, if I asked you to do that again, you guys could all do that, right? Right. This is where it's supposed to all come together now, okay? What we've been doing. It says find a point C or points on the given interval, -3 to +2, that satisfy the mean value theorem. Well, the mean value theorem says that the derivative is going to be equal to the average rate of change over that given interval. Well, what is the derivative? 3x squared plus 4x. What's the average rate of change over that given interval? 5. Derivative. So again, what we just satisfied was f prime of c is equal to f of b minus f of a over b minus a. That's what we just did, okay? And so we have this piece right here. We've set it up. We now want to find the x values, which will be our c values, where that's true. So I will solve for this. 3x squared plus 4x minus 5 is equal to 0. Now, I couldn't possibly make up problems that came up with rational solutions for everything. Too difficult to do. So I just referred to the quadratic formula on my calculator here. Somebody have a quadratic formula on your calculator that can give us these numbers with? .79 and so Sammy, I'm guessing maybe something got punched in different, or maybe the wrong program is punched in. I can look at it. But those are the numbers I came up with. And again, I knew that -3 1/3 wasn't correct. How did I know that? That's not in our interval. Very good. That would be outside our interval. Are these two within our interval? Yes, those two exist within our interval from -3 to +2. So those are 2 points that work. Now, my concern yesterday was that you didn't fully understand what these 2 points meant. That's where the graph has a slope equal to 5, an instantaneous rate of change equal to 5. So to make sure that we make that connection, here's what I ask you to do. Find the equations for the line's tangent to the function at point C. There are 2 points, so we're going to have 2 equations for the line. Then we will draw them on here and connect the whole thing together. So I have 2 equations. The first one, I need M, and I need a point on my line. Second one, I need M, and I need a point on my line. What is the slope of the first one? What is the slope of both of them? 5. The point on the line, the first one has an x-coordinate of 0.79. The second one has an x-coordinate of -2.12. How will I find the y-coordinates? Yeah, I'm just going to plug them in. Can't keep track of my calculators. Let's see. So we've got 0.79. The original function. The original function gives me the placement for where it's tangent at. The derivative would tell me the rate of change at that spot. I already know the rate of change at that spot. It's 5. So we plug in 0.79, we get 0.74. And then we get -2.12 will give us -1.54. Now I write my equations for my line. Y equals mx plus b. Y is 0.74 equals m, which is 5, times x, which is 0.79, plus b. I solve. 5 times 0.79. And then we would subtract that over. So I'll multiply it by -1 and add it to 0.74. I get b is -3.21. So y equals 5x minus 3.21. That is one equation for my tangent line. And then the second one, y, negative 1.54, equals m, which is 5, times negative 2.12 plus b. $9.06. So y equals 5x plus 9.06. This is where full understanding should come to be when we do this last part, okay? The directions say as follows. It says, draw a segment connecting the endpoints of the function. So I'm going to use my smartboard. I'm going to grab one spot here, and I draw a segment to right there. Can somebody tell me what's the slope of that segment? It is 5. Now, if I graph my two lines along with that, what should be true about those lines? And that's it. They should be parallel, tangent to the graph. They should never intersect. And that's what the mean value theorem really truly says. And this is kind of cool. If you graph this, negative 3.21, so I'm down 1, 2, 3.21. If you just think of trying to make a rough sketch, I know that this isn't exact science, but I think it's pretty neat how this ends up working. And we go over 1 and up 5. So over 1 and up 1, 2, 3. So somewhere right about there. If you draw the graph, you can see, you know, by just doing it by hand, those sure look like they're parallel at that spot. And if we graph them on our calculator, we would see that exact same piece. And if I take this one, which is y equals 5x plus 9.06, I go up 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh. 9.06. And then 5, I'm going to go down and back. So 1, 2, 3, 4, 5, and back 1, 2, 3, 4, 5, back 1. I mean, come on, drawing it freehand, I mean, this is remarkably accurate. And there we go. Look at that. Two lines parallel to the graph, exactly same as the average rate of change. Does it tie it all together? That's what it all means. Question. What's the point? Point is this. I am a cop. And I see Taylor Blake leave Albert Lee at 3 o'clock. He gets to Owatonna, where another cop calls me, says, hey, I saw Taylor Blake get up to Owatonna, or he's headed up to Owatonna. He says, yep, I just see him. It's 3:23. Oh, and what we say is, Taylor might say, hey, part of that time I was only driving 15 miles an hour. He could say, the majority of the time I was only driving 70. True or false? At some time, he had to be going over the speed limit. True. So, it tells us that at some time, you must reach that average rate of change. And that average rate of change right there is probably greater than that 70 miles an hour. So, tells us that Blake needs a traffic ticket.